our Twitch chat. Can we get some pods in chat?
Why are we on video?
Oh, Mackenzie can't be today. Oh, it's uploaded.
I bet you get one. Yeah, you're right. That's valid.
Yeah.
Student, yeah, student records. View grades, which should be on the side too. Grades. All right.
I'll give you your privacy.
But he's gonna give us I'm not sure.
Yeah, that's
Did you get an 18?
No. Actually, I have to turn on.
Yeah.
Here.
That one, well, no.
You have to wait for it.
What is?
Do you know if the library is open this weekend?
It probably is. I don't think they,
Is anybody else going home or no?
I don't think they usually go.
Everybody else going?
Personally, on Friday.
I don't think they usually kind of take breaks in general. You can watch it on the school website.
That's what I was wanting. I went to the home festival. Yeah.
Oh, yeah.
Yeah,
Was it
yeah, it was 3 pages.
20 and 60? Oh, they kind of got the. So I have a picture.
Yeah, I just disagree with this.
You said you have a plan?
It's like, I don't think, like, obviously I'm not gonna get any of PTSD if I didn't study, but if I got 3 out of 4, like, let's say, no in the class got 3 out of 4, like, but, because one person got only studied PTSD, and they could understand that, then they already have PTSD, versus me who, like, learned a bunch. But, you know, it, I just don't
Basically, like,
really.
if each one was more 25 points, you need the, ID only has 3 criteria.
Yeah, I
It should
just
still be worth 25 points.
don't think it's reflective of that burn.
I think that he assumed
It
that we
is
would study the most absolute ones, because like everyone else coming in.
So it's on the Thursday, Friday,
Yeah.
Because he said, he said that they were all fair game, which means each one of them has a chance to get. Why?
Which ones are
It makes.
I mean, yeah, we all. You know, like. I think you can make the argument for yourself. If you only work with it.
other day.
And then if you talk, you know, like you like to your lab.
Well.
Oh, yeah, you already said that.
Like five.
Water extension, right?
Yeah, back there, so I'll be there now, and it's not on top. Yeah.
Never.
He had land, and like, I really like,
Okay.
Yeah, no, I have, whenever she made the invitation, she was like, send this to all your friends. I sent it back to her. I was like, okay, so like, so, and.
friends of ours, but then like,
Yeah, a bunch of my friends who are really on the first one.
Like,
Like, I'm like with my ex.
email was like, well,
All my
we
people.
never said that we would accept
Very caravan.
And didn't email me back with
But I have two friends who do absolutely everything with, so I was like, would y'all want to go with John? No, they're like, yes, we have nothing to do with one holiday.
That's what.
because
Jake and Christina said they're coming. I don't know if they're
well, can call them. It's nice and direct.
We do have like, our problem's not small, right? Yeah, like. Doing people
It's
that
really
everything.
interesting because we know
No, we
that
understand. I really don't, so.
I didn't realize I was a Canada. I realized I was a Canada. I realized I was a Canada. I don't like that. I guess. Has my head been in it? Oh, yeah, it has. I can see my notebook. Yeah, it's been like that the whole time. Yeah. I just looked over and I was like, that's me. Feel bad I like punch over and everybody.
I just went there.
It's
I was literally like this. And I was like, what am I doing? That's terrible.
It's always whenever I like look up, because I'll be like this and I'll look up and I'm like, wait.
I'm a little gremlin.
Yeah.
That's how I eat too. Like,
Me, no, that's how I eat.
No wonder, like,
I used to have a teacher in elementary school that would give us posture packets if we didn't sit
Interesting.
like this. We literally used to have to write. And then if we like had our elbows on the table, she was the awful teacher.
My mom would walk up to me and she'll like pull my shoulders back. She'll be like, sit up straight.
I had to like stand against the wall as a kid, like, for like 10 minutes, to try to like.
Laptop.
I think I had pretty good posture because I'm short, so I like to.
I'm tall and I hate being tall, so I feel like I make myself shorter.
But my roommates, she has this thing where like pulls your back, it's like a full contraction, like she got on Amazon, like Velcro's behind you, and like pulls
I think
you
I
up,
know
and I
that.
was like, I need to get that.
Didn't one of y'all say something about?
Those sounds really nice. Yeah, I need it. But I can't.
You know, the backpack like things you lay on the floor. My friend had one and I tried it and it didn't work and I was so mad. I was so excited and I like laid there and I was laying on it and I started like shaking because I was like, I wanted to like crack it. I do it with my neck a lot. I know that's definitely. Oh, I broke my neck, so it cracked pretty. Yeah, probably. I broke it when I was like 10. I was swimming with my cousin. Jumping on my head while I was swimming. Yeah, it was in like May also, and I was so happy. I was like 10, so I couldn't swim the rest of the summer. Yeah, and my parents were at a party, so I had to lay in my bed for 3 hours to like go to take her to the hospital. It's all right now. I wasn't paralyzed.
Yeah, so I'm like, I don't think the next door. But you know what? It's Friday.
You know. And I was like, I know your customers are so scared.
And her dad was just walking out. He was like, 3 days to go.
Really appreciate
Trying
it.
to call her, our teacher was like,
Did you watch the something that I don't know? There's like one part of the season that I think defines like his general feeling all the time. It's like sideshow topic way. Yeah, just for a second, just one little like, he doesn't have time. Inside of me, there are 2 roles. I'm in the hospital because that is not normal.
All right, so what we're going to start now, so that was the one sample t-test. We're going to move into now to what's called paired samples t-test, or repeated measures t-test, or the dependent t-test. All right, here's the general formula for it. So a matched pairs t-test, or paired samples t-test, or repeated measures t-test, whatever you want to call it, is one in which you have paired samples, right? Often that is because you have like a pre-post design, right? So you measure somebody, administer maybe a drug, and then measure them again. And that's true repeated measures, right? Repeated measures are ones in which you repeat the measure within subjects, the same individuals. You can also run a dependent t-test where you have matched pairs, right? And that's the kind of design that I have here. We have matched pairs. So we have pair A, these are 2 individuals, all right? But we've matched them. Now, what do you match on? That's something I'm going to talk about in more detail later. But you match on things that you think are correlated with the dependent variable. I'll talk more about matching and what happens if you match on things that aren't correlated with the DV. But all things being equal, you want to match on things that you think are related to your dependent variable. So we have here, we want to determine if a new drug will decrease anxiety. Okay, we match subjects on current medication, age, severity of anxiety attacks. Then we measure the number of anxiety attacks for 1 week and take the mean for each individual, whether they got the drug or didn't get the drug. Right. So that looks like a straight up independent measures t-test, doesn't it? Right. And that's what we'll come back and talk about that here in a minute, which is where you have 2 independent groups. But these are not independent; they're dependent in the sense that we have matched each of these, right? So what we're going to use is what's called paired samples or dependent t-test for that, right? To calculate that, we use this t-test, right? We start by running difference scores, right? So I'm going to have you do this by hand here in a sec, but I'm going to get you set up with what you want to do. So I'll let you go ahead and do that first. So we need to run difference scores, all right? So we can run it 1 and 2. Again, some of those things is just going to change the sign of the T. It doesn't really matter to me. But most people we'll do 6 minus 5. Right, so look for 1. 8 minus 7, right? So on and so forth, right? So that's the first thing you got to do is you got to get your difference scores. I think the reason they do the second minus the first is a lot of times it is a pre-post design within subjects, okay? But again, it's one of those things that really doesn't matter. Then you're going to calculate D bar. What is D bar? It's the mean of the difference scores, right? So our T is D bar minus the mu expectation under null. If there's no effective drug under the null, we expect the mean of the difference score to be 0, right? Makes sense, yeah? Because the drug and no drug don't, or there's no effect of the drug, I'd expect the scores to be roughly the same, right? So while that's a long way of saying, you can put a 0 there, right? And so many times you'll just see the formula written as D bar over standard error. Okay? The D bar is just the mean of the difference scores. But don't lose sight that component is in there. Because remember, I had it up a minute ago, I told you all T statistics are based on some mean or mean difference minus the expectation of the null divided by error, right? Sometimes it's not easy to see. But I think Hal is going to write his formula like this, D bar divided by standard error. Right? So you get, yeah.
What is D bar once more?
It's just the mean of the difference scores.
It's just the mean of
Yeah.
the difference.
So it's just like you can go just like X bar, except they call it D bar because you have mean of difference scores. So you're going to calculate these different scores and get their mean. All right? Go ahead and do that for me real quick. And then we'll make sure we agree on D bar and then we'll go from there.
You said the negatives don't matter? Do they matter?
Well, it doesn't matter if you subtract no drug from drug or vice versa, as long as you're consistent. It's just going to change the numerator positive or negative sign, right? That said, most people are going to say 6 minus 5, 8 minus, that's why Hal's going to do it, right? Honestly, it does not matter to me. If you can say 5 minus 6, it's just going to flip it. So if it's negative one way, it's going to be exactly the same as positive in the other direction. At the end of the day, we're going to look at the means and see what differs from what, okay? So, but if you want to be consistent, the way I'll run it, 6 minus 5, 8 minus 7, and so forth. You get a mean for those scores. And that's the easy half, right? One of the things you're probably seeing is everybody agrees what the numerator should be, and that's the easiest. The denominators always give you problems, right? They're what require more work. Well, what do you do? All right. So this is standard error, estimated standard error of the difference scores on the bottom, right? To calculate this, I need the standard deviation of your difference scores, right? It's the standard deviation of the difference scores divided by the square root of n. This is the key. N is the number of matched pairs, okay? You do that, you can calculate T. And we'll go from there, all right? So everybody understand what you got to do, all right? D bar, then get the standard deviation of the different scores, and then that'll allow you to calculate standard error and calculate T. Right, so try to do that real quick. Let me know if you have problems, then I'll come around and have a look. I'm gonna set it up in Excel. I put these lines here because it's obviously very important that you stay on the same row, right? Because they're matched, so there's different scores matter. Or if you get stuck, feel free to talk or let me know if you're hung up. What do you guys get for D-bar? Very good, exactly. I agree. Degrees of freedom is equal to your number of pairs minus 1. And so, if you're familiar with independent measures T's, if you remember doing that, it would be n minus 1 plus n minus 1 of 2 samples. But in a dependent, you lose degrees of freedom, all right? So, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. It's 7 degrees of freedom. All right, a couple more seconds and I'll open it up and then we'll do it in SPSS 2 ways, right? So what I want you to realize, the reason we're kind of going through this and what I want you to see is, yes? What you got? Yes, exactly. So just treat these like they're X scores. Add them up and divide through by the total number of scores. Different scores are awesome. I'm about to put mine up in just a second. Yeah, you gotta have it.
Oh.
Yeah, so you put those in the column pull out. I'm about to put mine up in just a second. So one of the things that I hope you see is this is a paired samples t-test. A paired samples t-test is just a one samples t-test on the different scores. That's all it is. All right. In fact, that's exactly what we're doing. So think about what we just did as a one samples t-test. I took a sample and divided through by standard error. That's what I had you do over here. You calculated different scores and ran a one sample t-test. So a paired samples t-test is just a one sample t-test on different scores. Simple as that. That's all it is, right? So here's mine. I worked it out as well. Let me step out. So here are the data. Let me see if I can blow that up there. Better? So here is what I've got, the two sets of scores. Here are my different scores, okay? Here, next to the different scores. So subtracted the two out, okay? So you can see if you flip it around, the negatives and positives flip with each other, right? And the overall numerator shifts signs, okay? So right here, I'm just calculating deviations. So does everybody understand why it's C1 minus 1? Okay, what is, so for X scores, it's X minus X bars. For these, it's a different score, minus D bar. Is everybody with me? Okay, so what is D bar? I dropped it right down here. That's the average of your different scores, all right? So it is going to be 1 minus 1 is 0, 1 minus 1 is 0, 2 minus 1 is 1, 1 minus 1 is 0, 0 minus 1 is negative 1, so on and so forth. Right? In fact, if you ran these out, negative 5, negative 6, plus 6, and a bunch of zeros, still different. There's still deviations, right? So what do we do to that? We square them up, okay? So here, so this is, okay. So it's the sum of squares. This is just a one sample t-test. That's the whole point of doing this, is to show you that. So did you get 40? That's what I get for my sums of squares, okay? So here I've taken E9 divided by 7. That's the variance of the different scores, right? I took the square root of that, and that gives me the standard deviation of the different scores. And then I took E12 divided by the square root of 8, which gives me the standard error. This thing down here on the bottom. So I calculate standard error. And that is my attained t-value, right? So the attained t-value is 1 minus 1, so t is equal to d bar minus 0, because that's what the prediction is in the null almost always. Right? Without fail, it will be in this class, divided by standard error. Okay, so I get a t obtained is 1.18. If null were true, then based on the Excel function that I have there, my critical regions are this. So what about it? Reject or fail to reject? Fail to reject. If you don't understand why that is, let me know, because it will plague you on the next step, I promise. All right? You've got to be able to look and know if it's going to reject or fail to reject. So the value exists in this part right here in the middle, this section. So these are the cases that are likely under null. And for that reason, we're not going to reject them. Okay? Yeah, so it went up by a pound. Right? Not much. Could have been, right? In fact, let me show you a little something. Well, let's actually run these data first. Let's put them into, go ahead and drop them into SPSS for me, if you will. We'll do a couple of things here. More than two. Now, we don't have to actually take different scores and do one sample T. All right. Normally, I'm just going to run a paired sample. But I want to show you, I want to try to convince you that what we're doing is sound and makes sense. Does everybody have your scores in? Right? I just took these and dropped them in. Then remember how we compute something? I'm going to just do it inside of SPSS. Transform compute. We'll call it difference. And I'm going to say, take the difference of R3 minus 4 minus 3. I guess that's what I did earlier. Is that with me so far? I'm just computing different scores in SPSS. Same thing I did every time. And there they are. They're two different scores. Now, I'm going to run this t-test two ways. First is a one sample. Let's try it. right? You should know how to do that, so do it with me. Go to one sample. Test value. What's the expectation under the null? 0. One day somebody's going to do more than a list before. I still hear it. It's right or wrong, no matter how loud it is. All right, so yeah, exactly. So difference, test value is 0, right? I'm getting that right there. There's nothing to stop me from saying that the expectation would be 1 or 2, but it kind of sense is happening. It just doesn't happen. And in a paired sample, that effect size is 0, it's always going to be. All right, so we're good to go with that. T is 1.183. 0. Yeah, so we're getting that from the null. So the way I would write that is that T on 7 degrees of freedom equals 1.18. I usually write my T's only to 2 decimal places. P equals 0.275. Is everybody with me? That's APA for how you write a PT test, right? Like if you put it in there. T degrees of freedom equals P equals, and we get the P value, even when it's not significant. So way back, when I started out, we would just, if P was greater than 0.5, we just write P greater than 0.5. We don't do that anymore for the meta-analyses people. We put the actual P values in. The only exception are when they're really, really, really small, like 0.1501, right? That's the case, you put less than 0.001. So here's your mean difference. 95% confidence interval. I don't know if you can see that, but that's a negative and a positive. Okay. It contains 0, so I know I failed to reject by looking at the confidence interval. Okay. Same thing on these Cohen's D's down here. I'm gonna concentrate more on the Cohen's D's than the other. So that is a question I've asked on tests every once in a while, is that you have a set of data that are match samples or repeated measures, and your program will only run a one sample t-test. What do you do? Right? Well, the answer I would look for is I would take different scores and then run that through as a one sample with the different scores. That's the answer to that question, right? Because conceptually, that's exactly what you're doing, right? How would you run it? The way we'll normally run it, which is compare means, and then a new place for us, paired samples, right? I'll give you a second, make sure you get that. Analyze, compare means, paired samples. Okay. Look at it. I want my 2 variables, bar 3 and bar 4. Put them in. Options are nothing. I'll come back to this estimate effect sizes. Let's just run that real quick. All right, so here, this is new, so let me take our time to go through this. So what SPSS is going to give you is the mean of both groups. 7.1250, which is no drug, and 8.1250, which is drug. 2 standard deviations, 2 standard error means. You probably didn't even calculate that. If you calculated it based on my formulas, you didn't even calculate the means of the 2 groups because you didn't need it, right? That's the point I was trying to make, is that what you want to do is take those different scores. This is the correlation between the 2. That's an 8, which you'll look at the 0 up here. So this is the correlation. You would expect them to be correlated because they're repeated or independent measures, right? So that's fine. Paired samples. Tells you the same thing the other one did right there. There's your T, there's your degrees of freedom, there's your 2-sided P, which matches what I have written on the board over there. Okay. This should match your standard error. This is the standard deviation of different scores. That's the standard error of the mean for different scores. Okay. Any questions about that? Okay, and you got a confidence interval, right? Confidence interval, which is given to us right there. All right. That confidence interval, same interpretation we were talking about earlier, right? So it doesn't mean that that one contains it 95% of the time, but it's on the method, not on the actual. The probability is on the method, not on the specific. Well, are any questions about that? Does that all make sense? We're all good with that? Okay. Then let's go back to where we were. Compare means, compare samples. And then it says calculate standardizer using, what do you want to use, right? So let me talk about this just a little bit. I'm not going to read it to death. I'm not going to go into it in too great a detail. So the question, when you're calculating B, or estimated B, you have your mean and the difference scores, which is same thing as B bar, right? I'm just keep with Hal's notation. Now, I think he writes X bar with a little B subscript. So that's a mean difference scores, right? Is that right with me? Okay, same thing. That was called B bar up here. Just a different notation. Like that. Okay. So it's your mean for your difference scores divided by some standard deviation. What is the proper standard deviation is by no means agreed, right? And that's why you have at least 3 options there, and I'll give you a 4th, right? That's not actually listed, okay? Now, one thing is to use just that guy right there, which is the standard deviation of the difference scores. That's exactly what the default option is in SPSS. So it says standard deviation of the difference, right? So if you ran that as your default a moment ago, you got this standardizer down here. Notice it's 2.39046, 2.39046. So what I'm saying is, one way to calculate D is just to use the standard deviation of the difference scores. That's what we're doing here, right? The Hedges correction, the logic is the same. It just tries to adjust based on sample size. And it's particularly useful when you have small sample sizes. Yeah.
Why is the confidence interval different for this one if we ran it as an independent sample t-test if we're using the same subject?
So the standardizer here is, this is your confidence interval, this is your point estimate, is negative 0.418. I don't know what it was.
It's up there.
Here's your confidence interval. That's a good question. So we have, this is your confidence interval, this is the standardizer. So those two things are the same. I think it's going to have to do, so the reason the point estimate flips around is just SPSS's subtraction. So the t-value probably flips around as well, 1.183, negative 1.183. So don't pay any attention to that, but the values don't match up. So if it were to keep at that, you would have negative 3.2, or negative 3.2, yeah, to 1.131. Oh, I see. I was going to come up with an elaborate explanation, but I was convincing myself it's a 99%.
Oh.
That's good. I know. Let's go back though. It should, because you're right in your thinking, right? I was sitting there thinking, all right, so let's try that though. That's a good eye. All right. There it is right there. All right. So negative 320 to 1. Do you understand why it's flipping the negatives and positive? That's that arbitrariness I was talking about. So yeah, it should match up, right? And it does. All right. For that one. All right. We could also, is everybody with me so far? All right, makes sense, yeah? So compare means, paired samples. I could use the average of the variances. That's another one that Hal talks about in the text, right? So the average of the variances is exactly what it sounds like. Take the variance for the first group, variance for the first group, take the average, right? If we calculate D that way, we get a slightly different estimate, right? Instead of 0.418, it's 0.461, right? Another way, right? I could also calculate paired samples t-test, corrected standard deviation of the difference. It should tell you, yeah. So what we do here, that's really hard to read, I know, but it says Cohen D uses the sample standard deviation of the mean difference adjusted by the correlation between measures, right? So the argument was made a long time ago is that Cohen's D calculated with just the standard deviation for the different scores it needs to be adjusted because we know that these values are related to each other, not independent, like Cohen talked about. By their nature, they're related because we have matched them. Or we have the same person serving in both groups, right? And so some have argued adjusting the correlation or adjusting the standardizer as a function of the correlation. We're not going to go to the equations of how that's done, but it's a third way, right, that we can calculate it. That PDF, by the way, that I was talking about earlier, is this guy right here. This is in your that folder, Review Effect Sizes and Confidence Interval, Part 1 of the Cohen's family. If you, again, it's really more technical than I want to get into, but these repeated measures, here they are right here, there, and these are the things I'm talking about, okay? And if you, there's that correction factor, that's Hedges correction factor right there. If you work with somebody who works on effect sizes a lot, it's well worth the read, right? It really is. But it's not, it's the kind of thing that gets a little more technical than I want to get into. So I just put it out there as a resource. It's not something that's necessarily required. So what is the fourth way I can do it? This is a common one, right? And I think this is what Hal actually advocates in your text, is especially when you have like a, like a pre-post, right? So like, let's say a pre-post and you're measuring, I don't know, weight gain, right? Before and after some administration of a diet or whatever it is, right? Is to use the standard deviation from the pre-condition, right? That's something else that's also done, right? So what is the difference in weight gain divided, so take that divided by the standard deviation for your control, your precondition, right? There's 4 different ways that I know of to calculate Cohen's d, right? The problem is most people say we calculated Cohen's d, blah, and I have no clue what they actually did, right? Because to be honest, these aren't really Cohen's d. Cohen's d is a specific thing, the variations in Cohen's d. So my advice to you is this, and I don't think you can get in trouble doing this. First of all, pick what you're going to do before you start looking at the data, right? And then after you decided what you're going to do, just be clear. Say we calculated Cohen's d and we used blank as the denominator, right? And you can't go wrong with that, right? So you're being transparent about what you've done. And then go from there. Okay? That makes sense, right? So let's see. And to be honest, what I would actually do is probably use this Hedges correction, right? Because again, it really does, it makes an adjustment. You're really seeing the effects here nicely because I'm giving you small little toy data sets and so forth. All Hedges correction does is take Cohen's d, whatever way you've chosen to calculate it, and then takes that standardizer and changes it as a function of sample size to make it less biased for small samples. Okay. So what I'm going to do now, are there any questions about that? Paired sample t-test makes sense. Okay. So we have about 20 minutes left. One thing I want to do, I'm going to show you 2 things. One is I'm going to have you just make up a set of data that is statistically significant. All right. So what I want you to do is just take a blank data file. All right. And let's have 20 cases. All right. So I want 20. We're going to do this paired samples t-test. So can you come up, and then I'm going to actually use this to make another point I want to make. So make me a set of data here and here, such that if you run a paired samples t-test, there's a significant difference. All right? 3 or 4 minutes. Sitting there.
Yeah, but it's certain, better points.
Yeah, 20 pairs. 20 pairs. So give me 20 pairs of data. What about it? You guys do it? Yeah? How? So on one level, you're probably thinking, I need 20 scores that have a mean that differs from these 20 scores that have a different. That's one way to think about it. But a very simple way is to do this. What if I put, I'm going to make it real simple. What if I take 8, 8, 8, 8? I'm going to do 5 numbers. And over here I do 7, 7, 7, 7, and then 6. All right, so in all 5 of those instances, the second variable is less than the first, right? Do you know why? Do you understand why I didn't put 7 here? Does anybody want to take a guess at why I can't run that?
It's all the same.
Yeah, which means how much variability do I have? Won't run. Yeah, exactly right. So I gotta change it up a little bit. I gotta make some variation. Right? So if I do that and just go back to compare means, paired samples, t-test, throw those out. And we throw these in. It's all I needed. Right? So here's the thing. Is everybody with me so far? You see what my t is 6 on 4 degrees of freedom, 0.004. Okay? Why? You can actually have very few number of individuals or matched pairs or repeated measures. And if every single time one condition is always less than the other, you don't need much. Because remember, again, it's off the difference scores, right? When we do independent measures, T, we'll compare them directly to 2 means. And that's a little bit different. That's what we'll do next week. In fact, if I were to, let me just reverse these 2 right here. So all I've done is flip it, right? So now we have one indication of it going the other way, right? If I do that, I was going to have to blow it up. You see what I mean? All right, just that one flip the other way, right? So that's it. You know, this is one thing that in my own lab we run paired samples, t-tests. We use it a lot before we do LMs nowadays. But one of the things I learned a long time ago, and I remember when I learned about it, is that you can have really small effects, right? Yeah, I mean, we've gotten effects before where, you know, one class of words is maybe 5 milliseconds faster than another class. But it'll be significant if almost always a person shows that they're faster for one and slower for the other. You don't need a lot, all right? Because your data is indicating that it always runs in a certain direction. All right, so is anybody not able to get to 20? So if you get 20, it should be easy. And the easiest way to do it, the way to game it, is just always make one set higher than the other. Guarantee it's significant. Yeah.
So it says that it's significant with less than 0.031.
Yeah.
But in my confidence interval, it's not like this. So.
Yeah, no, you're right. Because remember that 0 is not contained in it. That's all on the negative side, right?
Yes.
Now, I will actually, next week, I have made up a set of data where I can actually have it be significant, and then the effect size, confidence interval indicates something else, but you got to kind of play around with it, and we'll talk about that. But for what you're doing right now, you should always agree, right? So what you're looking, another way of thinking about it, sometimes I explain it this way, is if the confidence interval has, so if we're looking for 0, the confidence interval has 2 different signs. It has to contain 0. Does that make sense? Negative. So if they're both negative or both positive, 0 can't be in it, right? But if you have negative and positive, then 0 is in it, right? And so for your example, they're both negative, right? Yeah. Yeah. What do you get? It's significant? Okay. Okay. Here's some comparisons, right? Show me your. that's not significant. And so you go back to your, all right, so run it for me, go analyze, go confirming. All right, so you got a difference, but it's not statistically significant. The reason is because you have, even though there's a difference there, you got some running one way and some running the other, right? So like what I was saying a minute ago, I could take your two means, I promise you, and find that they're statistically significant if I just made this number, whatever, what was your first mean? What was your mean for the first group? Like 13 something maybe? Or 18, or what was it?
13.
Okay, so if I can make these numbers 13 mean, and what was your other mean? All right, I can make these numbers 12.6, all right? Kind of like that exercise, you know, where I gave you guys, and I did one about what is the degrees of freedom, you could change them up. I can come up with a set of numbers where this means 13, this means 12, and it'll be statistically significant if I always make sure these numbers are larger than these numbers. You made that by making some larger on this side and some larger on this side, and they're canceling each other out. Even though the overall means are significant, you got enough variability within your difference scores that the t is not significant. That's what's happening today. Last thing I'm going to show you today is how to do this in Excel. Let's take some data. Let's make up some more data. Why not? So open up a blank Excel file for me. I use SPSS, or I'm sorry, I use Excel quite often for this because a lot of my job making out stimuli lists, right? So you might have a set of words that we want to vary on some variable. We want to make sure they don't vary on like 15 other things, right? And so I'll have like frequency for two sets of words, and then I'll run these T formulas at the bottom, and I'll code them like if it starts getting close to 0.05, like a significant turn red, so I can drop things in, just watch the numbers, right? So it's useful to be able to do. So let's make some data up. I don't know, let's go 8, 7, 8, 9. Sure. Right? And 6, 5, 4, 5, 6, 4. What do you think? Significant or not significant? No, yeah, that's fine. We desperately need a new projector in here. I thought in this class for what was on for the building. I don't know how many years that is. I don't know. What do you think? Significant or not significant? Let's find out. Equals what? T. Dot test. It's in, okay, you want to compare two sets of numbers? Which ones? That's array 1, comma, array 2, comma, tails, 2. Then it's going to say, is it paired? 2 sample homoscedastic or 2 sample heteroscedastic? You remember, did you guys go over homoscedasticity? Homogeneity of variants, any of those things ring a bell? That's, homogeneity of variants is the same thing as homoscedasticity. Right? We'll talk about that next week. That's just the assumption that in the population, the variances are the same for two groups. It doesn't apply here though. These might have two separate samples. That's really for independent measures to test. So right now, I'm just going to write 1 per pair. Okay. There's your p-value. That's what it gives you about this p-value. Okay. Gives you the p-value that compares those two. So am I cool with that? Makes sense? All right. So being able to run in Excel is also a helpful little thing, depending on what it is you do when you run these. I think that's it. We have just a few minutes left, but I don't have time to set up the next thing. So what we're going to do now, actually, I do want to do one more thing. Your book, I have a note in my notes to correct some stuff in your book. All right, so if you don't have your book, that's fine. But I do want to point out on page 197, there's a couple of errors in here that I noticed. So on 197, notice where it says the confidence interval is equal to X. plus or minus 1t times standard error, it's x bar. Right? That should be an x bar. Right? So we already know that, right? Because it's a sample statistic, nothing to do with data. That's on page 197. On page 200, oh, I'm sorry, it's not 200, it's 201. See that problem? Should be D bar. Okay, should be D bar. Is everybody with me? All right. There's another error a little bit later in this chapter, but I'm gonna wait and hold off until we get to where we understand what the error is. Any questions about any of that? Last thing we have to do in this chapter is finish up independent measures t-test. And so we do need to talk about things like homogeneity of variants, and what happens when you violate homogeneity of variants, right? Because that gets a little sticky, or you have to adjust your degrees of freedom and stuff. The formulas, by the way, for all of this going forward, or you have, so if you look in that canvas in chapter 7, this is something I'll talk about next week called variance sum law. This is what the independent measures t-test looks like that we're going to calculate. That's the adjustment that's made to the degrees of freedom when you have a violation of homogeneity of variants. We're going to have to do this stuff by hand. I just want to conceptually walk you through the idea behind sound grade adjusted degrees of freedom. All right, well, we will meet back. And once we get done with that, then we're going to put how away, and we're doing research methods and forms now that include all the knowledge jobs. Remainder of the next exam. All right, I will see you guys next week.
Bye, Mackenzie.